Our objective is to safely perform a classic displacement reaction by combining raw sodium metal with absolute ethanol. Bringing a burning splint to the mouth of the tube creates this distinct flash of fire, the physical confirmation that our reaction generated hydrogen gas. To perform this safely, you must wear safety goggles and handle the sodium metal exclusively with metal tongs. Successfully executing this protocol will show how the chemical structure of alcohol mimics the reactive behavior of water. Start with a clean laboratory workspace. Secure a test tube in a rack and pour in the initial clear liquid. It is critical that the ethanol you use is labeled as absolute, which means it is 100% pure alcohol. This split screen illustrates the danger of using common rubbing alcohol. Because rubbing alcohol contains water, the sodium will react much more violently and potentially cause an unsafe runaway reaction. Verifying this chemical purity is your primary safeguard when performing displacement experiments. Raw sodium metal is stored in oil to keep it stable. Use your metal tongs to extract a small piece from the container. Never touch sodium with your bare hands. The natural moisture on your skin will trigger an immediate chemical reaction upon contact. Use a scalpel to slice a miniature portion off the main block of sodium. For a safe reaction, size the piece according to this scale. The sodium metal should be no larger than a couple of grains of rice. Controlling the mass of the metal this strictly ensures the reaction doesn't create enough thermal stress to shatter the glass test tube. Now drop the sized sodium piece into the test tube of absolute ethanol. As the metal makes contact with the alcohol, you will see immediate, brisk effervescence. Watch the sodium closely as it reacts. You will see the solid metal begin to shrink and dissolve into the liquid. The invisible gas generated by this bubbling is now escaping the tube, so we must move quickly to the testing phase. This rapid bubbling indicates that the reactants are breaking down, creating the necessary conditions to capture and test the gas. Bring a burning wooden splint directly to the mouth of the test tube while the chemical reaction is still active. When the escaping gas meets the flame, it ignites instantly. This ignition produces a distinct pop sound, definitively confirming the gas is hydrogen. Successfully igniting the hydrogen proves that the chemical displacement has occurred. Looking back at the test tube, the liquid is now cloudy and contains a white solid. This white solid byproduct is sodium ethoxide. This diagram shows the chemical exchange. The sodium, marked here in blue, moves in and displaces the hydrogen atom within the ethanol structure. This reaction at the OH group is the same mechanic we see when sodium reacts with water. However, notice that the bubbling in the ethanol was less vigorous than what occurs with water. This shows that while the mechanism is identical, ethanol is less reactive in this displacement. The experiment is complete, leaving the stable sodium ethoxide at the bottom of the tube. We have successfully sized the metal, triggered the effervescence, and confirmed the hydrogen gas via the splint test. Now, dispose of the chemical byproducts according to your laboratory safety and cleanup guidelines. Using a controlled reaction to observe these displacement mechanics allows us to identify the shared chemical structures that define how different families of substances behave.